Okay, guys, we're going to be looking at the wave properties unit today, and this is our last AP unit in our year, so that is a good thing. And we're going to start off with a lot of definitions today. We're going to learn how to classify certain waves based on how they move and what they're doing. So first we have to define what a wave is versus a pulse, okay? A wave is a repeating and periodic series of disturbances that move from one point to another. Okay, so you see over here we have the same repeating pattern over and over again. That is a wave versus a pulse, which is a single disturbance traveling from one point to another. So you just get one disturbance in the medium, and then it wouldn't have the pattern over and over again. One of the most important things that you need to know about a wave is that a wave transfers energy but not matter. So if you pretended that this was a string or a rope with all the little parts and pieces of the rope connected together, the actual pieces that make up the rope don't change positions as you send a wave down through it. It just transfers the energy from one particle to another without actually changing their position. Okay, so I have a couple different simulations I want you to try. Okay, and first we could look at this one to show you just how the particles don't actually change position. So keep your eye on the green or the red. Like if this is a rope, these are the particles that make up the rope. Okay, and I could do an oscillation and show you. I'm going to slow it way down. Okay, and put it in slow motion. All right, so you can see the particles that make up this rope or string, and they're not moving their position. They stay locked in the same position, and they're just transferring their energy down the line. Okay, so waves transfer energy only, never matter. Okay, and we could also look at this simulation over here. I could switch from a pulse to a periodic wave. I could do the top view, so if this was like a sink filled with water and I had a drippy faucet, this is what it would look like. Or I could do a side view to show you what it looks like over here. So if I push the faucet on, you could see one pulse disturbing the water and creating a wave, okay, versus a periodic wave where if I put that on, you'll see it drips at a constant speed. That would be its frequency, and you would get the repeating pattern of the waves. Okay, so that's the side view. If you look at the top view, right, this is how they're showing it. So these bright spots are the highest points of the wave. They would be called the crest of the wave. And the dark spots down here, those are the low points on the wave. They are called the troughs of the wave. Okay, so I've embedded these into the assignment for today so you could actually play around with them and look at all different types of waves. Okay. All right, so along with actually knowing whether it's a wave or a pulse, you have to be able to classify the waves based on a couple characteristics. First off, you have to decide whether it's a mechanical wave or an electromagnetic wave. A mechanical wave requires a medium to travel through. Okay, without a medium, it wouldn't exist. So, a couple things we can think about here are water waves. Without water, they wouldn't exist. Waves on a rope or a string, those are mechanical waves. Without the rope or the string, they wouldn't exist. But the most important mechanical wave we talk about in this unit and have to calculate things with is sound. Sound requires a medium, whether it is a gas, a liquid, or a solid. It requires something to travel through. That's why one of the biggest mistakes in the Star Wars movies is that they're firing, you know, things and they're blowing up space stations and you're hearing all these explosions, but there's no air in space. So that sound wouldn't travel from where the explosion was to where anyone could hear it. So sound requires a medium to travel through. Therefore, it is a mechanical wave. Okay. All right. The other type of wave we're going to be looking at is an electromagnetic wave. This is everything that is on the electromagnetic spectrum. So radio waves, UV rays, microwaves, visible light, gamma rays, and everything in between. is an electromagnetic wave. They do not require a medium to travel through. And evidence of this is look at the sun. Well, don't look directly at it, but we get all types of radiation from the sun: X-rays, UV rays, gamma rays, visible light, infrared, and it can travel through the vacuum of space without a medium. Okay, so we know electromagnetic waves can travel through a vacuum. And when we're talking about a vacuum, it's always referring to no air. Okay, no air, no medium. Okay, so all electromagnetic waves, we could also refer to this as just EMR. EMR, electromagnetic radiation. All right, so along with defining things as mechanical or electromagnetic, you actually have to know how the wave propagates. And that's where we're going to look at whether it's a transverse wave or a longitudinal wave. The words you have to associate with transverse are perpendicular. All right, so with a transverse wave, the particles move perpendicularly to the speed or the energy of the wave. So this is a wave on a slinky, so it would be traveling towards the wall, but the actual parts of the slinky are moving up and down perpendicularly to the speed of the wave. So you have to associate transverse with perpendicular. Okay, and then longitudinal waves move parallel, okay, to the particles. So the velocity of the wave would be going left and right, where the particles are moving left and right. So, and if you look at what this is a tuning fork, and this would be a sound wave. A sound wave propagates as a longitudinal wave. So you should also note, a sound wave is a longitudinal wave. Okay, that's very important to know. And as the little tines on the tuning fork move in and out, they're compressing the air particles, and then the air particles in back of that are spread out. So, so that is called a compression and a rarefaction. If we were to draw that, sometimes they show sound waves as lines instead of those dots, but let's say we have our rarefaction like this, and our compression would be 3 lines together, then we would have 3 lines spread out, and then we'd have 3 lines together. So one complete wave for a longitudinal wave would be a compression plus a rarefaction. Okay, so that is one wave on a longitudinal wave. Okay, so compression is where they're close together. Rarefaction is where they're spread out. Okay, all right, so along with this, I'm gonna attach this YouTube video, okay, for longitudinal waves versus transverse waves, and I'm just going to speed it up to double time so you could get a little preview of it. But if we were in class, I would actually be demonstrating these waves with a slinky. So you saw how the motion was compressing. Now this is a longitudinal wave where the particles are moving perpendicularly to the motion. Okay? All right. So we're going to continue on with the anatomy of a wave. And the first thing we have to define is amplitude. Amplitude should be familiar from simple harmonic motion, and it's defined as wave height. And it's always measured from the rest position of the wave, which would be like the x-axis of the wave, to the highest point. Okay? Or the rest position of the wave to the lowest point. Okay? So both of those would be the amplitude of the wave. A common mistake is people think it's from the top of the wave to the bottom of the wave. That would actually be 2 times the amplitude. Okay, so just know it's always from the rest position to the highest point or the rest position to the lowest point. Okay, so looking at this, we have to know that a couple of the terms that are not in here are the top of the wave. This is known as the crest of the wave. And the lowest point of the wave, this is called the trough. of the wave, okay? And something that's really important is that it measures the energy of a mechanical wave, okay? So the amplitude of a wave is the energy of a mechanical wave. The greater the amplitude of a sound wave, the greater the volume of the wave. And the greater the amplitude of a light wave, the brighter the light. Okay, and you could think about that. If you have an amplifier on an electric guitar, an amplifier is there to make the amplitude of the wave larger so the volume increases, which should make a lot of sense. Okay, the next thing we have to define is wavelength. Wavelength is just how it sounds. It's the length of the wave. Okay, wavelength is the length of the wave. And there's a few ways to measure it. You could think of it as like 360 degrees on a sine curve. So if this is 0 degrees, quarter of a wave up, that's 90 degrees. Halfway through is 180, then 270, then 360. So you can measure one wavelength by moving 360 degrees on a curve, or it's also defined as distance from crest to crest. Okay, so if I go over on the top, that's one wavelength. Or if this wave was continued, let's say another half wavelength here, I can measure wavelength from trough to trough. That is also one wavelength. Okay, so it's one complete cycle of a wave. And frequency is a term we've definitely gone over before. Frequency is the number of waves or cycles per second. Okay, the unit for this we know is hertz. Abbreviation is Hz. And to calculate the frequency, we would count the number of waves and divide by time, just like we did previously when we maybe had some harmonic motion or circular motion. And if you look at our original wave, I'm going to delete the little part that I drew in. But if you look at our original wave, how many full cycles do we have? So we have one, and then we have a half. So this, as far as the number of waves or cycles, would just be 1.5. Okay, and then if we were given a time period, you would divide by the time. Okay, the next part is period. Period, as you know, is the inverse of frequency, and it's the time it takes for one cycle or one wave. And the unit for this, since it is a time, unit for this is seconds. And we have our typical period formula. Period is 1 over frequency. Okay, so this is the anatomy of a wave, and we're going to use a lot of these characteristics to calculate the speed and find the phase and things like that. Okay, so we're continuing on with phase difference, and 2 points are said to be in phase if they are one wavelength apart. Okay, or 360 degrees apart. Another way to say this is that they have the same amplitude and the wave is going in the same direction. Okay, so we have to look at the wave below to kind of decipher what that means. It's easier to tell if things are out of phase because you could basically get that right 90% of the time, and then you have to really think if they are actually in phase. So we'll start with point A. Okay, think about the criteria that point A or any other point has to fit to be in phase with point A. So 360 degrees apart, so that's one full wavelength away. So A to B is 90 degrees. So ready? 90, 180, 270, 360. So E is also in phase with A. Okay, you can also look for other points that are in phase with A. You just have to be another 360 degrees apart. So 90, 180, 270, 360. So A, E, and I are all in phase. Okay, so let's think about point B. Which points are in phase with point B? Remember the criteria. They have to be one wavelength apart, which is 360 degrees, or have the same amplitude and be moving in the same direction. Okay, so B is very easy to tell. So B has the same amplitude and is the same part as the wave as F, as is J. So B, F, and J are all in phase, right? Let's look at C, right? C is like the midway point of the wave, all right? So C is not in phase with A, even though they have the same amplitude, okay? Remember, they have to fit both. They have to be the same amplitude and moving in the same direction. A is on the upslope of the wave, where C is on the downslope of the wave, okay? So you have to find same amplitude on the downslope. So this is the upslope. So G is on the downslope, as is K. So C, G, K, all in phase. All right, the last one we could do is D. D is in phase with H. Okay, they're the same amplitude on the same point of the wave, 360 degrees apart. All right, so if you're not in phase, then you're out of phase. Okay, out of phase. And another thing we have to do is be able to tell how many degrees a point is out of phase on a wave. So for instance, if we took point D and point, let's say G, how many degrees separate D and G? So we just add them up. So 90, 180, 270. So these guys are 270 degrees out of phase. All right. What about H and G? Well, not H and G. That doesn't make any sense. I pointed at F. F and G. F and G, they are 90 degrees out of phase. Okay. So to count up the phase difference, you have to look at how many degrees are separating the points on the wave. Okay? All right. The next part is calculating wave speed. Okay? This is a very important part of our unit. Wave speed is simply calculated by multiplying lambda, which is the wavelength measured in meters, times the frequency. And remember, frequency, yes, we use hertz as the honorary unit to name it after and honor hertz, but it's really equal to 1 over second. So if you look at what we're multiplying, we have wavelength in meters, frequency in 1 over second, so that gives us the unit for speed, meters per second. Okay? And a couple of these facts are really important. Okay? First off, the speed of a wave in a medium depends on the properties of the medium. Okay, so whether we're traveling through air or water or a solid material, the speed of the wave will depend upon the medium it's traveling in. Okay, the next bullet point is probably the hardest concept in this unit and the next unit, but it's probably the most important. The speed of the wave is constant in the same medium. Okay, so if you have a wave and it's traveling in the same medium, it will always have the same speed. Okay, you have to think about this because it's going to be one of the more important things we deal with throughout the unit. And it may not make sense now, but hopefully as we go through it over and over again, it will start to click. So in a couple pages, we're going to be doing problems about electromagnetic radiation in the form of radio waves. Okay. Radio waves come in all different frequencies. That's actually how you get your radio stations in your car. You maybe never realized it, but like, for instance, Z100 is 100.3 megahertz. Hertz is right there. That's a frequency. Mega means million. So this is an actual frequency that the radio station is vibrating a signal out at 100.3 megahertz. And whether you're listening to this radio station with this frequency or you're listening to, like, do I know any other radio stations? 106.1 megahertz. Okay. They have two different frequencies. They would have two different wavelengths. But since they're the same type of wave, they would have the same speed in the same material. Okay. And I can't stress that enough, that that is one of the most important concepts we do in this unit as well as the next unit. Okay, a number that we have to know. I'm going to erase that highlighter there. A number that we have to know is the speed of sound in STP, standard temperature pressure. Okay, STP, we have to know, most important, is 0 degrees Celsius because temperature is going to play a role here. But the speed of sound at STP is 331 meters per second. Okay, if the temperature is not stated, we just default to STP at 331 meters per second, and we'll need that in a lot of our calculations. All right, and the speed of light. So that's any electromagnetic wave, anything that's on the electromagnetic spectrum, whether it's gamma ray, infrared, microwave, visible light, whatever it is. The speed of any electromagnetic wave in a vacuum is 3 times 10 to the 8th meters per second. This is the speed limit for all things in our universe. Nothing can travel faster than the speed of light. Okay, so if you're getting numbers for speed that are way bigger than the speed of light, you've done something wrong. All right, so these facts are pretty important. Hopefully they become more clear as we go along, but just try to accept them for now, and as the concept comes up again, we'll touch on these characteristics again. All right, direction a particle moves in a medium. For this, I'm going to show you a PhET animation, and hopefully you could see the direction the particle moves as it travels through a medium. Okay, so to define a couple things in here, first off, we're going to do the fill-ins. As a wave travels through a medium, the particles in the medium vibrate. The particle appears to go in a direction opposite to the motion of the wave. Okay, so if you look at this is actually a pulse traveling through a rope, and the velocity of the wave is going to the right. Okay, and we have to decide which way will point P on this wave moves as the wave travels through this rope. So the wave energy is going to the right. Which way will particle P move? Will it move up? Will it move down? Will it move left? Will it move right? Okay, well, one of the things that you could already eliminate is whether it's moving left or right. Remember, this particle on this wave, it's not going to travel down the wave as, it's moving along. It is tethered to that point. It's not going to move left or right. So you can eliminate that for a transverse wave or a transverse pulse. Okay, so our options are moving up or moving down. And to do this, you have to look at the wave or the part of the wave that's coming next. Specifically, the crest of the wave is coming next. So in this part, as the wave travels through, the next part of the wave that's going to hit it is the crest of the wave. So this one would actually move up. Okay, I'm going to show you the PhET now so you could do this for yourself. Okay, I'm going to show this oscillating string. I'm having it fixed on one end. I actually might do no end. Let's do no end. We're going to have no damping, so we're not going to have any loss of energy. Frequency, maybe I'll make the amplitude, I don't know. I'll keep it here. And I'm going to start the wave, let it get going, and then I'm going to pause it and kind of step it through. So I'm going to let the wave go. This is slow motion, so we can see it a little bit clearer. You're starting to see that sine curve traveling along. All right, I'm going to pause it. I want you to keep your eye on one of these green dots. Let's focus on this green dot right at the center, okay? This way we can keep our eye on it. And remember, the wave motion is going from the left side of your screen to the right side of your screen towards that door. So in your head, think about what is the next part of the wave energy that's going to hit the spot. Is this green dot going to move up or is it going to move down? And as I step the animation through, you can see that the wave dot is actually going down. So the next part of the wave that hit that dot we were keeping our eye on was the trough of the wave. So it went down with the wave energy. Okay, let's focus on this one right now. Okay, this green dot. What part of the wave is the next part that's going to hit this wave as the wave is traveling from left to right. Okay, and make your prediction. It's not going to travel left or right. All right, it's either going to go up or down. So what part of the wave is next? And as I step it through, you see that the next part of the wave was the crest. And now the crest hits the particle and it goes up. So a lot of things to keep in mind here. The fact that the wave transfers energy, not mass. So these dots aren't traveling down the rope. And also that you have to look to the next part of the wave to kind of figure out which way is it going to go. And I could let it play out and you can see, how the wave moves and how those dots aren't moving left or right. They're just going up or down. And play with this on your own and kind of make assumptions and try to see what happens, because this is kind of a hard concept for some students. Right, so applying the same knowledge, now we're looking at the next example with point P. Which way will point P move? So look at the wave speed. It's going from left to right across your screen. The next part of the wave is going to be the trough. So that point P is going to go down. And they didn't really tell us where to stop, but it's going to go down, and then it's going to go up, and then down again. But we'll just say down for now. Okay, I hope that made sense, and you play with the PhET simulation. All right. This is one of my favorite conversations to have in class. And we go over this old-time saying, keep your ear to the ground. What does that actually mean? Okay, keep your ear to the ground. Well, usually when people tell you that, it means like, look out for things coming your way. And the reason that this should make sense is because when you keep your ear to the ground is a solid material. Why might it be better to listen through a solid than through air that is a gas? And this is related to how sound waves travel through different media. Okay, so sound waves traveling through different medium. Think about the difference between a solid, a liquid, and a gas if we're talking on like an atomic level. Okay, if you picture a solid, you should think of very tightly packed molecules all together. Liquid, are there more space between them? Gas, it's almost completely empty space. Okay, so if we're thinking about how sound waves travel, what they have to do in order to send the signal, this atom has to crash into this atom, has to crash into this atom, and so on and so forth. So if you have tightly packed materials like solids are, you would have that information traveling more rapidly than you would through a gas. So this is why this not very bright person is having their head on a railroad track waiting for the train that is clearly in the distance. He can hear the train coming through the solid material before he could hear it coming through the air. Okay, so sound travels the fastest through a solid and the slowest through a gas. Okay, and we have some of those bits and pieces of facts in here. So the speed of a mechanical wave, so something that requires a medium. So the speed of a mechanical wave depends on how quickly one particle can transfer its motion to another particle. Solid particles respond much more rapidly to a disturbance than gas particles because they're much closer together. So we have some facts. So speed of sound at STP is 331. Speed of sound in a material such as aluminum is 5,100 meters per second. So a huge difference between the speed of sound. Okay, and then we have the speed of sound also depends upon the temperature of the medium. And you'll actually have to do some calculations based upon the temperature of the medium. And it's specifically for gas. So we actually have a conversion here. You have to add 0.6 meters per second per 1 degree Celsius, whether it's going up or down. So plus or minus 0.6 meters per second per degree Celsius. So you start with our STP speed, and then you change it based upon the temperature. Okay, so commit that one to memory. That one does not show up on a reference table of any sort. All right, so other important things. The frequency of a sound, okay, sound wave. corresponds to its pitch. And we went over this one before. The amplitude of the sound corresponds to its volume. Okay, amplitude, amplifier, energy of the wave, they're all related. All right, conceptual question over here. What happens first, the thunder or the lightning? Okay, how can you tell how far a thunderstorm is from your current location? So we also talk about this. You should know that you always see the lightning first. You always see the lightning first. If you think about the speed of light, which we could actually use lowercase c because it has its own variable because it's so important and so specific. 3 times 10 to the 8th meters per second. It's like a million times faster than the speed of sound. Okay, speed of sound, 331 meters per second. So you see the lightning first and then you hear the thunder crash after it. And if you've ever tried this when you were younger, or even I still do it today, you count between the lightning flash and the thunderclap. You go 1 Mississippi, 2 Mississippi. If you take the time, let's say there's 3 seconds between the lightning and the thunder, and you want to know the distance the storm is away from you, we could use our old average speed formula. Average speed is distance over time. You could solve for the distance by taking, if you want to get really specific, you could actually calculate the speed of sound based upon the temperature. And you would find out that's 993 meters away. Okay, and then we would convert this if we wanted to know in 1 mile. There are 1,609 meters. So if the lightning storm is 3 seconds away from you, okay, that's a little over a half a mile. That is 0.62 miles away from you. So it's time to go inside and get away from the thunderstorm. Okay. All right.